Installing software is becoming obsolete. Not everywhere, not tomorrow, but the idea that serious software must belong to Windows, Mac OS, or Linux is starting to look strangely old. Open Figma. That design tool runs from a link. Open Photoshop in a browser tab. Google Earth works there too. No installer, no operating system choice, no machine cluttered with another updater that launches every time you restart. The browser is becoming the universal software platform. And the technology making that possible is not JavaScript. It is WebAssembly. That sounds like another version of the headline you have already seen. WebAssembly is replacing JavaScript. It is not. JavaScript still controls the page. It handles the interface, talks to the DOM, and loads WebAssembly in the first place. WebAssembly is replacing a different assumption that powerful software must be rewritten for the browser, usually in the browser's one native language. The browser used to be a place where you visited websites. It is becoming a place where software lives. That shift is much bigger than a language fight. The browser spent roughly 30 years speaking one programming language. JavaScript earned that position. It ships in every browser, runs without installation, and lets anyone turn a plain document into an interactive application. But JavaScript was designed for web pages, not desktop-grade software. Modern engines have pushed it remarkably far. For forms, content sites, dashboards, and most business applications, performance is rarely the problem. Then developers started putting video editors, games, design tools, and 3D engines in browser tabs. That is where the compromise becomes visible. These applications often begin as large C++ or Rust codebases. Rewriting all of that software in JavaScript would be slow, expensive, and difficult to maintain. Figma faced this early. Its editor was written in C++, so the team compiled it into asm.js, a restricted version of JavaScript designed to run efficiently. It worked, but the browser was still pretending the C++ program was JavaScript. WebAssembly stopped the pretending. A compiler can turn C++, Rust, Go, C#, or another supported language into compact bytecode. The browser validates that code and executes it inside a protected sandbox. The program is not translated into JavaScript first. For the first time, the browser had a serious second language. But the first version of WebAssembly came with an uncomfortable limitation. It was excellent for languages that managed memory themselves. It was much harder for almost everything else. Java, Kotlin, C#, Dart, Scala, and many other languages rely on garbage collection. The programmer creates objects. The runtime tracks them and frees the memory when those objects are no longer needed. Early WebAssembly did not provide that kind of managed memory. A language could still compile to WASM, but it often had to bring its own garbage collector. That added weight and complexity before the application performed any useful work. Then WebAssembly 3.0 arrived. Its most important feature has one of the least exciting names in computing: garbage collection. WebAssembly can now provide the low-level managed storage that language compilers need. Those languages no longer have to solve the whole problem inside every application. The release also added native exception handling, tail calls, multiple memories, richer reference types, and 64-bit memory addressing. Old WebAssembly memory was limited to 4 gigabytes. With 64-bit addressing, browsers can support memories up to 16 gigabytes, while standalone runtimes can go much further. That matters when the browser is opening a huge design file, loading a serious data set, or running software that once expected an entire workstation. WebAssembly 3.0 did not suddenly make every language equal inside the browser. It removed several of the reasons they could not compete at all. Java, Kotlin, Dart, Scala, and OCaml now have practical WebAssembly paths. Microsoft's Blazor lets developers build browser interfaces in C#. Unity and Unreal can export experiences to the web. The browser is no longer asking every language to become JavaScript before entering. That changes who gets to build for it. Think about the last time you installed a large desktop application. You chose the correct operating system, downloaded a large package, accepted a list of permissions, waited for the installer, restarted something. Then the application introduced its own updater. The browser offers a much cleaner deal. Click a link. That simplicity used to come with a clear trade-off. Websites were convenient, but native applications were powerful. WebAssembly is narrowing that gap. Figma can reuse high-performance C++ code inside its web editor. Photoshop can place serious image processing software inside a tab. Game engines and CAD tools can target the browser without rebuilding everything around JavaScript. WebAssembly also runs inside a sandbox. Native software can receive broad access to a computer. A WASM module starts with tightly limited capabilities and can interact only with what the host exposes. That restriction is part of what makes the browser trustworthy enough to become a software platform. A link can deliver complex code without automatically giving that code the keys to the machine. This is the part I find genuinely exciting. WebAssembly is not merely making websites faster, it can make powerful software easier to access. A student does not need the correct laptop installer. A collaborator does not need the same operating system. A user can open the application from a link and begin working. The browser becomes the compatibility layer, but WebAssembly did not stay there. The same qualities that make it useful in a browser also make it useful in places with no browser at all. A WebAssembly module does not assume that a browser exists. At its core, WASM is a safe, portable code format. A browser can host it, but so can a standalone runtime on a server. The missing piece was access to the outside world. Server software needs files, clocks, network connections, and random numbers. WebAssembly provides none of those capabilities automatically. WASI, the WebAssembly System Interface, gives a host a standard way to offer them. The module receives only the capabilities it needs. A program can access a particular file without gaining permission to explore the whole machine. It can open an approved network connection without inheriting every capability of the host system. WASI 0.2 also made the component model stable. A component written in Rust can communicate with one written in Go through a shared interface. The languages do not need to agree on every detail of each other's runtime. Fastly compares these components to Lego bricks. That idea puts WebAssembly into direct competition with containers. A container packages an application with the operating system files and libraries it expects. WebAssembly can package the program inside a much smaller sandbox. For long-running services, containers remain an excellent answer. For short-lived functions, edge workloads, plugins, or customer-supplied code, WebAssembly can start faster and use less memory while maintaining strict isolation. Cloudflare, Fastly, and Fermyon have built edge platforms around that model. Docker supports WebAssembly workloads. Kubernetes can schedule them beside traditional containers. In December 2025, Akamai acquired Fermyon. The technology that began as a way to run C++ in a browser is now being purchased as cloud infrastructure. The browser was not the limit. It was the first convincing demonstration. WebAssembly appears on only a small portion of the web. It cannot directly control the DOM through a standard browser interface. JavaScript still connects WASM modules to the page. Debugging is less comfortable. Tooling varies by language. Compiling an application to WebAssembly does not automatically make it fast, small, or well-designed. Most websites do not need it. A form is not improved because its validation was rewritten in Rust. A CRUD dashboard does not need a second language simply because the option exists. JavaScript remains the easiest answer for a huge amount of web development. Desktop applications are not disappearing either. Some software needs deep operating system integration, strong offline support, access to specialized hardware, or an interface too complex to treat as a server-connected web page. WebAssembly does not erase those needs. It changes the default. The browser is no longer limited to lightweight websites written in one language. It can host serious software compiled from many languages, while the same code can run on servers and edge platforms outside the browser. That is why calling WebAssembly a JavaScript killer undersells it. JavaScript is one language. WebAssembly challenges the boundary between websites, desktop applications, and cloud software. My advice is simple. Do not rewrite an ordinary web application just to use WASM. Watch the places where installation, portability, isolation, or raw computation are the product. That is where the change will appear first. And here's the question I want developers to argue about. If a browser version and a native desktop version offered identical performance, would you ever install the desktop app again? My answer is no. I suspect a lot of developers will hate that answer.